Let's minimize our functional by applying ordinal least square method. Before we had a derived, uh, we had a functional that we derived earlier, and that large function was dependent on b beta 0, 1, and 2, and we need to minimize our function. To find minimum, we start by calculating derivatives of our function with respect to each of the variables, with respect to b1, respect to b2, and respect with b0. Derivative with respect to b1. To find the derivative of the sum of difference, we can derivative each term separately, partial derivatives, and then add the results. Let's take the first bracket, an expression of the form. Let's imagine we have one object right here, and this is our last function of that particular object. We have these two features. We have target value here that we subtract from our prediction, and three coefficients. This is power function squared. To differentiate it, we have to extract the power of 2, reduce it by 1, and the square disappears, leaving a multiplier of 2 right here. Since this is a composition functions, we apply the chain rule. We have to multiply by the derivative of the inner part. Inside the linear function of b, partial derivative of b1, its derivative is simply the coefficient of b1, 23. So our derivative of the function will look like this. Now I added a few more objects. You can see that we don't have just one object that we had before on the screen. Now we have two more objects. They basically the same. The same logic is here. So we can focus just on this particular part. And what we do, as I already told in the beginning, first of all, we place our square right here as a multiplier in the beginning of parentheses. And also we had our partial derivative had a coefficient of 23. So according to chain rule, we also put it right here. And we do the same. We place our coefficient of every beta 1 coefficient, we place it right here under parentheses right here. So this was chain rule, and this is how we found our derivative function. Partial derivative, if to be correct, for variable beta 1. So, but we don't have just one variable here. We have to find partial derivative for every of our variables, the independent variables, for our dependent variable q. So we can do the same for all of our partial derivatives. We can do the same for beta 2, beta 0, applying the same rule, but this time we look at beta 2 as our partial derivative, and this coefficient will be moved on the front. So like this, we can build system of equations, and by solving this system of equations, so we are trying to find such beta 1, beta 0, 1, and 2 coefficients that coefficients that will get our derivative function equals to 0. It means extrema point, minima or maxima point. And we won't solve this system of equations right now. We will simply take answers. The answer will be 5 minus 30 and minus 45. So is it a minimum maximum? We need to check the second order conditions, calculate second derivatives as we did before, and apply Sylvester criterion, Hussein, matrix of Hussein. Since we don't want to show long calculations, we can just directly say that function is concave up, convex at this point. Therefore, we found minimum point. So our parameters 5 minus 30 minus 45 such points on the graph of quality functional that it's this quality functional is minimal. So basically, yes, this is the same answer of these three beta coefficients are the best possible coefficients to explain how our features x values dependent on y on the graph. So we apply this to our prediction hat y. We apply 5 with x1 minus 30 multiplied by x2 minus 45 as our intercept free term, and we can actually substitute this x1 x2 with any of our objects in dataset and get prediction. So this kind of final result that we would like to see as our model can predict values. My stock price is 40 and I have my debt is 1 million. Tell me what is the price will be next year. So we substitute x1 equals to 40, x2 equals to 1 million, and we get the forecast that equals to 125. So this is how our model works. It might be very tricky to calculate all these partial derivatives and solving system of equations and then applying Sylvester's criterion to find the best possible minimum point of our quality functional. It's too long and it's too complicated for calculation. So instead of that, we will use something different. And now I will introduce matrix form, and we will use matrix form here. Why it's needed? We have a problem with the current method, and we just have two features. And imagine we have 100 feature, million objects. We won't be able, never be able to calculate such things on the paper. So we will use matrix form of the same thing. So instead of each object separately expressed by separate object on line, we can write this as a vector of our features and vector of our coefficients. And this is the way how we can rewrite our calculations in a more beautiful and simple way.